All right, so we're going to continue with section 13.1, and we're going to work some exercises out of y'all's textbook, starting on page 823. So we'll start with number 19, which says in exercises 19 through 23, sketch the graph of f, and they give us f of xy equals x plus 2y. So first we're going to change this f of xy. We can replace that with z. So we can try to get this in a more familiar form to figure out what it is for the sketch. And some of these I'll sketch, some I will just describe. So I'll go back and forth between the two things. So here, let's put everything on one side. This is the same as x plus 2y minus z equals 0. We'll put all of the, if we had some constant term, we would leave the constant term over there, but our constant, we don't have any constant terms in here though. So we can see now this is a plane with normal vector n equals 1, 2, -1. And for planes, if we had something other than equals 0 here, I would sketch it. For planes, you only see me sketch ones that have points on all three coordinate axes here. For instance, if I were to plug in x equals 0 and y equals 0 to try to find what's on the z-axis, I'm going to get z equals 0 as well. So I can't get the points on the axes for all three axes is just the point on the axis is just the origin. So there's nothing. This would be kind of difficult to sketch. You kind of got to sketch it based upon the normal vector. And even after you do that, it's not very easy to tell that it's the plane that you want it to be. It just looks like any old plane that you sketched. So we won't sketch planes like this. We'll sketch some where you can plug in x and y equals 0. You're going to get z equals some number. You can plug in y and z equals 0. You get x equals a number. You can plug in x and z equals 0. You get y equals some non-zero number. For all of those. Otherwise, you'll just identify that it's a plane, and you can write down what its normal vector is. All right. So next, let's look at number 22. Which is f of xy equals the square root of 4x squared plus 9y squared. The square root of 4x squared plus 9y squared. So first we're going to write this as z equals the square root of 4x squared plus 9y squared. And now, to put this in a more familiar form, I'm going to square both sides, but I have to keep in mind that this right here, the square root, is always positive. So when you square both sides of an equation, you're actually adding on information, and I don't want that additional information. So z squared equals 4x squared plus 9y squared. This previous line, the function we were given, z was always greater than or equal to 0. So I need to specify that there. That I'm using this to figure out what this looks like, but I need to keep in mind that z is always greater than or equal to 0, because according to this, z doesn't have to be greater than or equal to 0. If I plug in -3, whatever I would have where z is -3 is the same thing I would have z is +3. So there's no restriction on z being greater than or equal to 0 here, whereas that was the initial restriction we were given. So we have to maintain that restriction. All right, so now we'll use our traces that we talked about in the last lecture to sketch this. So let's start with the trace x equals 0. And remember, for your traces, you can use whatever you want to. You're just trying to get information about what the graph's going to look like at the end. So for the trace x equals 0, when we put that in, we get z squared equals 9y squared, or z equals plus or minus 3y. All right, so let's sketch that trace. Now, keep in mind that z is always greater than or equal to 0. So this is going to x equals 0. We're in the yz plane. But to make sure I don't accidentally draw some negative z values, I'm not even going to draw the negative z axis. All right, so z equals plus or minus 3y, so up 3 over 1. So we would have something like that. And then the negative of that. So that's what we would have for that trace. So now let's do another trace. And you'll always see me do a trace x equals, then a trace y equals, or a trace z equals. I don't tend to do like 3 x traces. I'm not going to do x equals 0, x equals 5, and x equals 9. I would do, you can do that, but normally you're going to get plenty of information from just doing one for each variable. So let's look at the trace. Let's do z equals 6. Now, how did I choose 6 of all numbers? So I chose 6 because I looked at 4 times 9. 4 times 9 is 36. So I want this to also be 36. I just want to be able to divide by, when I divide both sides by 36, I want to have some fractional value, something that's less than 1 here. So when I divide by, if I divide the whole thing through by 36, this would change to x squared over 9. This would change to y squared over 4. And this would be 1. And that's really what I want, is I want a 1 over here. And I want those things to come down so that I can be in a familiar realm, conic sections, and I can have what's called an ellipse. But if you put something else in other than z equals 6, it still works out fine. It's just I pick something where I would have 1 over something here and 1 over something there. You whatever, pick z equals 2, for instance. You pick z equals 2, you're still going to divide everything through by 4 to make that a 1. And then you're still going to have an ellipse regardless. All right, so let's look at z equals 6. When I put that in, I get 36 equals 4x squared plus 9y squared. So now I want this to be 1, so I can see that it's in a standard form of an ellipse equation. So this is 1 equals x squared over 9 plus y squared over 4. Now this is an ellipse, and if you're not familiar, if you don't remember conic sections or not familiar with conic sections, don't worry yourself about that. Just look it up in the back of the book, but don't dig into the details of it. You just need to know the basic things, like be able to identify, okay, it's a sum of x squared and y squared, and it equals 1. That thing's an ellipse. If it was a difference of x squared and y squared terms, and you have to have equal 1 as well, then it would be a hyperbola. And that's really all you need to know. But there are a lot of other things about conic sections that you won't need to know, so just brush over those things. All right, so now let's sketch this. And we're not actually in the XY plane, so we'll put little parentheses there and there, because we're actually in the plane z equals 6. All right, so now you're just going to take, if you kind of want to know what this thing looks like, which way it's elongated in the x direction or y direction, I just take x equals 0 and y equals 0 and plug those in to see. So when I take y equals 0 and I put that in there, I get x equals plus or minus 3. You don't need to do this in as much detail though. When I take x equals 0 and I put in there, I get y equals plus or minus 2. So it's elongated in the x direction, or the x axis, what's called the major axis, but you don't need to know that terminology either. So, because we just want rough sketches. This is not our final sketch. This is just helping us figure out what we have in the end. All right, so now, what we want is we want to try to put these two things together in 3 dimensions to see what it is that we get. So let's sketch our coordinate axes. Now, one thing, this doesn't have anything to do with the sketch right now, but just a note from our last lecture is that if this truly were the XY plane, like this is where Z equals 0, then this would be called a level curve. Remember, level curves are when you take, and actually it'll be a little bit clearer when I make my sketch, when you take your whatever trace you would have and you kind of just smash that thing down into the XY plane. But because I would just put the parentheses there to indicate it's not actually the XY plane. Had I left those off, that would have been fine. I just need to know that that thing is a level curve. So that was just a side note. So now in the YZ plane, it's going to look like this. So remember, in 3 dimensions, don't sketch any arrows on there. So we'll have something that looks like this in the YZ plane. I'm going to try to be kind of accurate. So before I sketch that, actually, let's do this one for accuracy purposes. So now if we were at Z equals 6, then we would have an elongated ellipse in the X direction. So let's do that first instead. So we have, say something like that at X equals 6. All right. So now we can kind of see where this is going to come in the YZ plane. So we would have that there and that there. And then we'll just shade this in. And that will be our 3-dimensional image that we got from using those traces. And what is this called? This is called an elliptic cone. All right. And you might want to say like elliptic cone that opens up or opens right or opens left. This one opens up in particular. All right, so next. Let's look at number 23. Which says that, so same directions, f of xy equals x to the 1/3. So f of xy equals x to the 1/3, or z equals x to the 1/3. All right, so one thing to note here, and it's not just about this problem, but in general. So when a variable does not appear in a function, the function is placing no restrictions on that variable, and it takes on every value. So when you start a problem like this and you don't see any y's in there, your immediate thing should say, that you should write down should be y takes on every value. So here, well, I'll write it down here since it's after our note. We would say for this one, I'm not put it up here, y takes on every value. And we've discussed this before when we were talking about cylinders. So now it's true in general when we have the graph of a function. So now let's start with what does this look like in the trace of y equals 0. So the trace y equals 0, that's the xz plane. And this would look like that. And for something like this, if you don't know what it looks like, go to like Desmos, DSMOS.com, and just put it in there. And so you can see what that thing, what it looks like in 2 dimensions to help you figure out the 3-dimensional thing. All right, so now, but whatever you get from me, whatever you see in the textbook, they should be fairly familiar. So now what we do is now we're going to sketch this in 3 dimensions, and we're going to drag this thing along the y-axis because y takes on every value. But all we're going to do is just take this and drag it, and that'll give us what our actual 3-dimensional shape is, or our 3-dimensional surface is. Let's see which way. So we're going along the y-axis. So should I draw this? Let me come over here. All right, so now we're going to sketch 2 of these, one at the left, like right here through the origin, one at the right, and then we're going to connect those 2 things. So let's sketch one here first. And it kind of look like a little dotted. I may fill this in a second, but just in case, I'm going to make it dotted for now. Remember, don't put arrows on your 3-dimensional sketch. And I'm going to sketch the same thing over here. Oops, I already messed it up. I kind of want them to look identical, and just that I slid it over. And now that I've done that, I'm just going to connect those 2 and connect those 2. So this would be, our surface would look something like that. Probably should have skipped on the shading part. So that's what that thing would look like, something like that. Now, what is this? What would we call this? Whenever you take something, this 2-dimensional curve, and you just drag it along some axis, and it doesn't have to be like the coordinate axes. Like I could say I'm dragging this along whatever that is, I'm dragging it along that. I'm just dragging it in the y direction, basically. So it's making a sheet in the y direction because I'm dragging in the y direction. So we would call this thing whatever your function is that you have. So here we have the cube root function. So I would just call this a cube root sheet. Or you might see cylinder sometimes, but you're going to hear me use sheet. So I would say this is cube root sheet. And just to be descriptive, I'll say along the y-axis. All right, so we'll stop this video here and then we'll continue and do some more examples from 13.1 in the next video.